In this lecture, we will discuss some special type of LPP problems. Basically, we will discuss few things, three different things. First, we will discuss about the alternate solution or infinite number of solutions. Then we will talk about the unbounded solution, that is whenever the solution is unbounded. And number 3, we will discuss about the degeneracy, whenever degeneracy occurs, how to come out from that. These three things we will discuss now. The first one is the alternate solution. If you remember, we have told one thing, that is Zj minus Cj, Zj minus Cj, if this is equals 0 for basic variables, Zj minus Cj should be equals to 0 for basic variables, and Zj minus Cj should be greater than 0 for non-basic variables. In general, for optimality, Zj minus Cj should be greater than equals 0. So, Zj minus Cj should be 0 for basic variables and Zj minus Cj should be greater than 0 for non-basic variables. So, this we will see. Let us take one example for alternate optimal solution or the maximum or infinite number of solutions. Let us consider one problem. Maximize Z equals x1 plus 2x2 plus 3x3 subject to x1 plus 2x2 plus 3x3 less than equals 10, x1 plus x2 less than equals 5 and x1 is less than equals 1. So, first we will write it as in the standard form, as we have done. The inequalities are less than equals type. So, I have to introduce 3 slack variables and to make these inequality constants as equal. So, in standard form we can write down maximize Z equals x1 plus 2x2 plus 3x3 subject to x1 plus 2x2 plus 3x3 plus x4, this is equals 10, x1 plus x2 plus x5, this is equals 5, and x1 plus x6, this is equals 1. And of course, your xi or xj are greater than equals 0 for j equals 1 to 6. So, at first you are introducing 3 slack variables x4, x5 and x6, and you are making the less than equals type inequality into equality, so that your initial basis will be x4 equals 10, x5 equals 5 and x6 equals 1, where x1, x2, x3 are 0. So, therefore, in the basis your variables are x4, x5 and x6. So, I am writing here x4, x5 and x6. So, these are a4, a5 and a6. Your Cj values are normal, that is 1, 2, 3, and for x4, x5 and x6 the values are 0. So, your Cb values will be 0, 0 and here 0. Now, write down the rows, that is 1, 2, 3, B value is 10, 5 and 1, 10, 5 and 1. So, this will be 1, this will be 2, this is 3 and x4 is 1, x5, x6 are 0. For the second one, x1, x2 is 1, x1, x2, then x3, x4 are 0 and this is 1, x5 is 1, x6 is 0. Whereas, for the last one, x5, x1 and x6 coefficients are 1, all others are zeros. So, you calculate now Zj minus Cj, that is Cb into Xb minus Cj. So, Zj is Cb minus Xb minus Cj, that is this coefficient value. If you calculate, you will find it will be minus 1, minus 2, minus 3, and these 3 will be zeros are there, so 0. So Zj minus Cj is less than 0, and most negative is this one, most negative is this one. Therefore, your entering variable will be x3 in the next iteration. So you have to calculate the ratio b by yrj. Y means I am talking about the values of the coefficients. So this will be 10 by 3, and these two cases infinity. So the question does not arise. So only one minimum, that is your departing variable will be x4. So in the next column, your departing variable will be x4 and entering variable will be x3, that is x4 will be replaced by x3. So from here, if you see, your entering variables are becoming x4 will be replaced by x3. So x3, x5 and x6 are coming here. You are having a3, a5 and a6. One more thing, that is in the earlier one, this is x3 is the entering variable and x4 is the outgoing variable, departing variable. So your pivot element is this one, that is 3. Pivot element is here 3. So that I will make 1, and all other elements of that column will be 0. Your Cj values are same, 1, 2, 3, 0, 0, 0. So that now x3 has entered, so it will be 3, 0 and 0. Here it will be, I am just directly writing 10 by 3, 1 by 3, 2 by 3, it will be 1, 1 by 3, 0 and 0. Here it will be 5, 1, 1, corresponding to this element will be 0, 0, 1 and 0. Here it is 1, b value is 1, then this one will be 1, 0, 0, 0, 0 and 1. So this will be the next table, and here if you see, in this case your Zj minus Cj value will be 3 into 1 by 3 minus 1, so this will become 0. This is also becoming 2 minus 2, so this is also 0. This is 3 minus 3, so this is becoming 0. After that it is 1, it is 0 and it is 0. So in this case, if you see, all Zj minus Cj is greater than equals 0, so there is no need of calculation. So Zj minus Cj greater than equals 0, but Zj, if you note here, Zj minus Cj, this one is not greater than equals 0, not greater than 0 for non-basic variables x1 and x2. Please note this one. I will come to this point that Zj minus Cj is equals to 0, not greater than 0 for the non-basic variables x1 and x2. So in this case, your optimal solution will be, in the basis you have only one decision variable x3. So in the basis your solution will be x1 0, x2 0 and x3 is 10 by 3, sorry, x3 is 10 by 3. So therefore your x3 will be 10 by 3, and value of z or z max, maximum value of z you can obtain from here as z. So at first you are obtaining the solution for Zj is greater than equals 0. Zj minus Cj is greater than equals 0. But we also note one thing, that Zj minus Cj are 0 for two non-basic variables x1 and x2. Thus, we can make two different tables again by entering one as x1 and entering another table I can make by x2, and I can get some other solution. That means we want to say here is that if I change from here x3, x1 and x6, The values will be A3, A1 and A6. Your Cj is same 1, 2, 3, 0, 0 and 0. So that here it will be 3, 1 and 0. So your B values are, you are just making it 5 by 3, 0, because you have entered here 5 by 3, 0, 1 by 3, 1, 1 by 3, minus 1 by 3 and 0. This column will be 5, 1, 1, 0, 0, 1, 0. This will remain unchanged, and this one will be x6 corresponding to x6. It will be 0, minus 1, 0, 0, minus 1 and 0. So, from here by replacing x5 by x1, and the reason is your x1 and x2 are non-basic variable in the optimum table and their value is 0. Therefore, if I replace in the basis one variable by either by x1 or by x2, I will get other solution that we are checking. By replacing this, if we calculate again Zj minus Cj value, you will find that all these are 0, 0, 0, 1, 0, 0. That means Zj minus Cj is greater than equals 0. Therefore, you can tell that other solution is x1 in the basis now, x1 and x3 are present. So, x1 is 5, x2 is 0 and x3 equals 5 by 3. They are satisfying the constraints, and if you calculate the z value here again, in that case again z value is 10. So, optimum value of the objective function remains same, it is unaltered, that is its value remains 10, but the feasible basic feasible solution changes or the values of the decision variables changes. So, this one table I have shown where by replacing the non-basic variable x by some basic variable, I am getting alternative solution. Similarly, if I replace some variable of the basis by the another non-basic vector x2, then I will obtain another solution. And since I have obtained two solutions, now any linear combination of these solutions also will be a solution. So, but the value of the optimum value of the objective function will remain same. That means, we want to say that suppose your x1 here is this point, x1 is this value I am taking 0, 0, 10 by 3, 0 x1 is 0, 0 and 10 by 3, and x2 I will take 5, 0 and 5 by 3 say, because already we have seen that x2 is 5, 0 and 5 by 3. So, since these two are the solutions, so any convex combination of these two will also be a solution of this one. That is, any convex combination means lambda I into x1 plus 1 minus lambda I into x2. That will also be a solution where lambda lies between 0 to 1. Suppose we choose lambda 1 equals half. In that case, I can obtain another point x3 by using these combinations. I can get 5 by 2, 0 and 5 by 2, 0 and 5 by 2. This is also another optimal solution, and the value of z max at this point will remain the same, that is z star. Or if I choose lambda 1 equals 3 by 4, in that case I can obtain another solution as 5 by 4, 0 and 35 by 12. And in this case also optimum value of z remains same, that is 10. Therefore, for this particular case, what is happening if you see here is we have the optimum solution, but the number of optimum solutions are infinite. So, if I have to find out by finding two solutions, from there I can generate optimum number of solutions by changing the value of lambda, where lambda lies between 0 to 1. So, this is one case where you can obtain infinite number of optimum solutions. The second case comes is the unbounded solution. The second point is unbounded solution. Let us see what is unbounded solution in this case. Let us take a problem, a minimization problem we have taken. Z equals 3x minus 2y subject to x minus y less than equals 1, 3x minus 2y less than equals 6. Since it is minimization problem, so at first I have to write it in the standard form and I have to make it maximize. Z star will be equals to minus 3x plus 2y, because you know that maximum of z equals mean of minus z. Here we have two less than equals type constants. So, we have to add two slack variables over here to make the equations as inequalities. So, subject to x minus 1, x minus y plus, say I am taking z, this is equals 1. Another one is 3x minus 2y plus w, this is equals 6, say, where x, y, z and w all are greater than equals 0. So, all are greater than equals 0. But therefore, what is happening in the standard form, since it was minimization problem, I am converting it into maximization problem, that max z star subject to these two equations, where inequalities are replaced by the equalities by adding the slack variables. Now, let us apply the simplex algorithm to check what is happening over here. So, in the basis, the variables will be z and w. The initial basic solution, feasible solution will be z equals 1, w equals 6 and value of x and y are 0. So, in the basis your z will come and w will come. So, I am writing this A3 and A4. Your Cj values are minus 3, 2, coefficient of z and coefficient of w are 0. So, you can write down 0 into z plus 0 into w in the quadratic, in the objective function. So, your Cb is 0 and 0. B values are 1 and 6. So, it is 1 minus 1, 1, 0. Next one is 3 minus 2, 0 and 1. So, now we calculate the Zj minus Cj, that is Cb into Xb minus Cj. So, the values you will obtain as 3 minus 2, 0 and 0. So, in this case, your entering vector is basically y. Your entering vector will be y and it will be replaced by which one? It will be replaced by the ratio b by xj. So, but in both case if you see, first one is 1 by minus 1, that is minus 1, and in this case also it is 6 by minus 2, that is negative minus 3. So, both are minus 1 and minus 3. So, but as per theory which we have told earlier, xbr by yrj must be your, this ratio should be greater than 0. So, the computationally this should be greater than 0. It cannot be negative, and if this xbr by xbr by yrj value is less than 0, then there will be unbounded solution. What it means actually? That means if we start increasing the value of y, then the value of the objective function z will go on increasing indefinitely, because there is no change or no other variable is coming departing from here. If you see z equals 3x minus 2y, this is your objective function, and this will decrease to minus infinity if you make y approaches plus infinity. If y increases, z equals 3x minus 2y will approach to minus infinity. That means, as you increase the value of y, value of the objective function will go on decreasing. So, there is no minimum value of this. Therefore, for this case the solution is unbounded. You will obtain unbounded solution, means there is no optimum solution you can obtain, and the reason is also quite clear from here, that whenever y is approaching plus infinity, in that case the objective function decreases to minus infinity. That means, if I go on increasing the value of y, z will decrease like anything. So, I do not know where it will finish. Therefore, the solution will become unbounded, and this will be quite clear whenever, if I try to think about the graphical case. Your problems are x minus y equals 1, the constants if I say, and x by 2 minus y by 3, this is equals to also 1. So, if you try to draw something like this over here in this case, then if this is the point 1 0 0 minus 1, so one line will go like this, and there will be another one that is 2 0, and this is the line x minus y equals 1, and this will be another one 0 minus 3. So, there will be another point something like this, which is the line 3x minus 2y equals 6. So, if you try to see the feasible region from here, feasible region will be on the positive axis, that is positive x axis, y axis, and the lines bounded by this. So, this region. So, it is not feasible region itself is not bounded. So, please note this thing, feasible region is not bounded means the solution will be unbounded. Therefore, in the ratio, that is xbr by yrj, if it is less than 0, always we will obtain the unbounded solution. So, this we have to remember. Our third point is the degeneracy. Usually, degeneracy occurs when one or more of the constraints are redundant. Here, redundancy means we want to say that degeneracy occurs means constraints are redundant, means if I do not write down a particular constraints, then also the nature of the problem will be unaffected or the solution will remain unaffected. So, please note that usually degeneracy occurs when one or more of the constraints are redundant. Degenerate basic solutions are basic solutions with one or more basic variables at 0 level. So, if the problem or if I have redundant constraints, in that case the basic solution which you will obtain, you will find that the value of one or more basic variables is equals to 0. Existence of degeneracy does not ensure improvement of the objective function at each iteration of the simplex algorithm. Please note this point. If degeneracy exists, then there is no guarantee, it does not ensure that objective function value will improve at each iteration of the simplex algorithm. That means, it may happen that you are going on doing iteration and instead of improving, you are coming back to the same solution afterwards. Suppose you have a solution of maximization type simplex problem be degenerate. That is, we have a basic feasible solution where a basic variable is at 0 level. we are assuming that for some k not in the basis iteration, your Zj minus Cj is less than 0 is most negative for at least one Yik greater than 0. So, for some ak which is not in the basis in this current iteration, Zj minus Cj is less than 0 and which is most negative for at least one Ik greater than 0, or in other sense your ak or the vector xk will enter into the basis, since Zj minus Cj is most negative for that value. Therefore, hence according to simplex procedure, in the next basis ak is the entering vector. Now, the value of the objective function will be which one? Z new equals Z old minus x br by yrk into zk minus ck. Note this one, old value, this is the iterative value, will be changing Z old minus x br by yrk into zk minus ck. Now, if yrk is greater than 0 and x br is equals to 0, x br means we are saying that the element which is in the basis is 0, because we have assumed one thing, that is whenever degeneracy occurs in the basis or in the basic feasible solution, in the feasible solution you have one basic vector whose value is 0. So, therefore, your yrk is greater than 0, it has to be greater than 0 and x br is 0. So, whenever x br is 0, that means this term, if you see this term vanishes. So, therefore, z new is equals to z old, or in the other sense no improvement in the objective function. Therefore, please note this thing, that whenever degeneracy occurs, usually degeneracy occurs due to the redundant constraints, and whenever degeneracy occurs, it may happen that in iteration after iteration you are not getting any improvement in the objective function. So, this is one thing, that it does not, degeneracy does not ensure that there will be any improvement in the value of the objective function in the iterations of the next iterations of the simplex algorithm. So, in the next class we will see other property, that is cycling of the degeneracy.